What's up, bitches? Today we're going to learn regenerative Rankine cycle, okay? On screen over here is the simple Rankine cycle. That's the TS diagram. And the TS diagram for regenerative cycle, it's based off of this. There's just a little extra steps. And depending on which type it is, it's going to look different, okay? So you either have open feed water heater or closed feed water heater. Your open feed water, it's just a little bit more like simple than the closed feed water. It starts at 0.1, it goes directly up at 0.2. Then it's gonna touch the saturation lines over here. Go up even more. Then it's gonna go like this. 0.5. Then 0.6 is somewhere over here, hold on. 0.6. Then down over here at 0.7. This is your open feed water heater, regenerative Rankine cycle. Basically what happens is, after 0.5, after going into the turbine, some of the water is gonna get into the open feed water heater and combine into 0.3, okay? What you have to understand here is that at 0.2 and 0.6, the mass combines. Usually in your problem statements, they're going to write over here y. Y is a fraction. That it's usually less than 1. It's like basically a percentage. So one, like a part of your mass goes through here and the other part goes over here, 1 minus y. Okay. Like if you add both of these, it's equal to 100% of the mass flow rate. Basically what this means over here is that the mass flow rate at 0.2 plus mass flow rate at 0.6 combine at 0.3. And using the energy in equals energy out formula, you'll find out that H2M2 plus H6 times M6 equals H3M3. For a lot of your problems, you're going to have to use this formula over here. Other than that, the principle is exactly the same. Wherever you see vertical lines, work is being involved. So both of these lines over here, it's W in. And both of these vertical lines over here is W out. The reason why it's hard to calculate W out and W in is because you don't have 100% of the mass that's being involved at these points, okay? Usually in your simple Rankine cycle, the entire water is moving across the TS diagram. So you just do the delta H. But for example, for W out, you have to take the mass flow rate over here, M5, and then H5 negative H6, and then plus this part over here, so M7, H6 negative H7. Because of this complicated, you just have to keep in mind how much mass it's flowing, okay? That's why the Y is important, and they put it in all of your problem statements. Whenever you're calculating the work or the heat, you have to keep in mind these things, okay? Just know that beyond 0.3, 0.4, and 0.5, the mass flow rate is like at 100%. All of the water is moving through here. Next, wherever you see a curved line, heat is being involved. So Q in over here, Q out over here. You don't need to calculate this part over here unless if your problem says so. Because this part over here is your, it's like internal, it's within the system. No heat is coming externally from the environment to influence your system. And that's it. Usually to find W net, a lot of the problems you're going to see, they use Q in negative Q out. This is the same reason as I said before. It's because like over here, there's the mass flow rate being like part of the mass is being extracted like into the heater, so it's a little harder. So they use this equation generally. And over here, like I said, Q out, you have to take into consideration the mass flow rate. So it's equal to 1 minus y times the total mass flow rate times the delta H, H7 negative H1, and that's your open feed water heater. All right, for your closed feed water, it's a little bit more complicated, but it's not that hard. You start at 0.1, go up to 0.2, then somewhere over here it's going to be 0.3, goes over here, 0.4, 0.7 is over there. I'll explain in a second. 5, and then lastly 0.6 is over here. The reason why 0.7 is over here is because they're taking the simple Rankine cycle as reference. That's why it's like at an odd place. It's just because the extra step is over there. And in a lot of your problems, you're going to see this line over here. It just explains that some of the water enters over here, but you don't need to know that. It's nothing. Just know that after 0.5, a fraction of the water is going to go into the what do you call it? The closed feed water heater. Ideally, 0.3 and 0.7 are completely horizontal. That means it's the exact same temperature, okay? T3 equals T7. Just pay it. We just have to know this TS diagram by heart, and you'll understand that, oh, here it's horizontal, it's the same temperature. So unlike the open feed water, the water at 0.2 and 0.5 combine at 0.3 and 0.7. They don't combine at one place like the open feed water. It's a little different over here. Using the E in equals energy out formula, you'll get M2H2 plus M5H5 equals M3H3 plus M7H7. You have to know this equation by heart. A lot of the problems that you're going to solve, you have to know this. You have to use this equation basically. And the rest is exactly the same. Q in is over here. Q out is over here. Wherever you see like curved line, that's heat being involved. And where heat is being involved, ideally you're assuming no work is being done. So it's constant pressure. Down over here too, constant pressure. Same thing with over here, constant pressure. Here, the feed water. Wherever you see vertical lines, work is being involved. So work in is over here, and work out is over here. And just like your open feed water heater, you have to pay attention to how much mass is being involved. That's why you have to take into consideration the Y over here. Y is basically like the fraction. It's supposed to be a percentage of how much water is going into the heater. And over here is the rest, 1 minus Y. And that's it, super easy. All right, so now let's do an example just so we understand a little better, okay? So I highlighted whatever is important in this question. It just says that there's a closed feed water heater, gives us a bunch of temperatures and pressures. And then it's asking us to find all of these values over here. So the first thing that you do when you get to your exam or whatever, you have to read the question entirely, okay? You see over here, there's the turbine isentropic efficiency, for example, and then the rest is not really important. It is, but not for now. The first step that you do when you solve this problem is you have to draw the TS diagram. That way, you don't get lost, and also you're probably going to get partial credits in your exam when you draw something like this. So since it's a closed feed water heater, we have 0.1 over here, 0.2, 0.4, and over here, see it says isentropic efficiency. So for example, hold on, let me draw this. Ideally, it's going to be beyond 0.4, it's going to be a straight line, ideally over here. But since there's an isentropic efficiency, it's going to look more something like this. 6, 6. That's it. All right, so now we're ready to write everything out. P1, T1, T2, T2, T3, T3, T4, T4, T5, T5, T6, T6, T7, T7. All right. Every time it's asking you to find W in, W out, whatever, almost like all of your questions, you have to find the H, the enthalpy for all of these points. So let's read the question. It's saying plant maintains a turbine inlet at 3 MPa, whatever. It's over here, the turbine inlet, 0.4. So 3 MPa, 350 degrees Celsius. Keep in mind over here, it's Q in over here. There's no work. We're assuming there's no work being involved. That means it's constant pressure. So P3 equals P4. So over here also 3 MPa. And operates a condenser at 20 kPa. 20 kPa is over here. Constant pressure, right? So P1 is 20 kPa. It's equal to the same as P6, 20 kPa. Steam is extracted at 1 MPa. That's over here. After, whoops, this is supposed to be 0.5. 0.5, there's constant pressure at 1,000, at 1 MPa. So 0.5, 1 MPa, and pressure 7 is 1 MPa. The rest is discharged into condenser, blah, blah, blah. And that's it. And then we have the isentropic efficiency of the turbine to be 0.9. All right, so now we have to find all of the H's, okay? So let's look over here. At 0.1, it's on the saturation lines. So we just have to take into consideration the pressure, and then you have to read your water tables to find the saturated fluid temperature, HF, at 20 kPa. So reading the tables, we see that it's equal to 251.42. 42. So over here, you're going to write 250, what? H1 equals 251.42. Next, to find 0.2, you don't have the pressure or the temperature. You don't have nothing. You do know over here it's a straight line, so there's work being involved. You have to use the work equation, which is equal to the specific volume times the pressure difference. You have the pressure difference at at 0.2, actually, technically, you do have the pressure. It's over here, 3 MPa. Keep in mind that wherever you see curved line, there's like heat being involved, and you're assuming there's no work done. So all of this point, it's the same pressure. That's why I wrote CP, constant pressure. So to find the specific volume, again, you just have to read the tables. We know that 0.1 is a constant, sorry, it's not constant, it's like a saturated fluid. So VF at 20 kPa, you see reading the tables, it's equal to 0.001017. So your work is equal to 0.001017 times P2 negative P1. So again, for this equation, the work equation, you have to use kPa. So 3000 kPa negative 20. Calculating this, you get a work of about 3.03. You also know that work is equal to H2 negative H1. And we have H1. It's 251.42. So H2 equals 3.03 plus 251.42. Adding those numbers, you get H2 to be about 254.45. So over here, we're going to write H2 equals 2, hello? Holy shit. $254.45. Whenever you're dealing with these problems, usually you won't get anything at 0.2 like to go off of, unlike your other cycles. So you almost always have to use this. Whenever you see like a straight line going up, take into consideration this equation to find the H2, okay? Next, at 0.4, we have the pressure and the temperature. So we just follow the table, the superheated tables, to read H4 to be about 3116.1. Okay. Now, reading 0.4, you could see it's a turbine and the rest goes straight down. It's the same S, ideally. So also you have to mark down your S. S4 is equal to 6.745. Okay. I'm going to write up here in our table where H4 is equal to 3116.1. All right. Now we could get started with the at 0.5 and stuff, okay? At 0.5, it says over here, P5 is equal to 1 MPa. So you have 1 megapascals and saturated, or entropy at 6.745. You have to check your superheated tables, and then you have to interpolate. So I'll write you the interpolate. Holy shit, what the fuck? H is equal to H1 plus the slope. This shit works. Plus H2 negative H1, S2 negative S1 times the S that we have, negative S1. Okay. So plugging in all of the numbers, that you could see on screen over here, you're going to get an ideal enthalpy, to be about 2852.9. I'm not going to write out the entire equation. You just have to interpolate basically. This is ideally if the turbine's isentropic efficiency is at 100%, the straight line over here. Us, it's a little bit more like diagonal over here. So what that means is this. Where the bottom is ideally at 100%, okay? That means 0.9 equals to H4, which is 3116.1, negative our actual H5, divided by 3116.1, negative what we just found in the tables, 852.9. With this, we could find the actual enthalpy at H5 to be about 2879.22. We're gonna write this on our table over here. H5 equals 2879.22. All right, you're gonna do the exact same thing for 0.6. We have 0.6 to be 20 kPa, and then S6 to be about 6.745. Now, if you check the superheated tables, you'll see that you're not gonna see the, like, everything is gonna be way like above 6.745. That means over here we drew it wrong. It's not superheated, it's not outside the curved line, it's inside the curved lines. When it's outside the curved lines, it means it's superheated, but when it's inside, it means that there's a quality to it. There's the X. The equation for the X is equal to S negative SF divided by SFG. We need to find X. We have 6.745. And then reading the tables at 20 kPa, you see that the SF is equal to 0.832 and SFG to be equal to 7.0752. Calculating this, you get an X of about 0.8357. Now with this, you can find H, which is equal to HF plus the quality times HFG. Reading your tables and plugging in all the numbers, you get you get your ideal H6 to be about 2357.5. This is ideally if the entropy stays the same for 0.45 and 6. However, since we have the turbine efficiency, you have to use the same formula again. Equals to H4 negative H6 ideally. So 0.9, you already have H4, which is 3116.1, negative H6, which is what we're looking for, negative the ideal enthalpy, 2357.5. Solving this, we get our H6 to be about 2311.03. H6 equals 2311.03, sorry. Now for 0.7, you just have to check that T3 is equal to T7. Okay? What you have to do is, well, usually, unless if the problem states otherwise, which it doesn't say anything, 0.7 is on the saturated lines. And we know that over here, it's given that it's 1 MPa. So you just go to your tables, you see where it's 1 MPa, and you have to read the fluid enthalpy at 1 MPa, which is equal to about 762.51. And you get the saturated temperature of about 179.88 degrees Celsius. So now finally you can use this to find 0.3, because we didn't still find the enthalpy at 0.3. You can't really find it. It's in the middle of this curved line over here. You have to find 0.7, the information at 0.7 first to find 0.3. So we know that T3 equals to T7 at 179.88, and P3, as we wrote in our table up over here, is equal to 3 megapascals. 3 PA. Once you check the tables, you'll realize that it's like, once you check the superheated tables, you'll realize that the temperature is below the saturated temperature. That means that it's subcooled water. You have to check your tables for your subcooled waters and then interpolate. However, personally, when I was taking this class, I didn't have the subcooled water tables. So instead, you have to approximate. The way you do that is you just ignore the pressure, because the enthalpy doesn't, when it's subcooled, the pressure doesn't really affect the enthalpy. You just have to check the temperature. The temperature is exactly the same as, like, you're not going to get 179.88 in your degrees Celsius in your tables. It's going to be at the 1 MPa pressure tables, okay? When you read your tables, as you can see on screen over here, the temperature is like the same as what we just looked at T7. So you approximate H3 to be about 762.51. When you do this in your exam, write a star approximated using T3 equals 179.88 degrees Celsius. When you do your exam, make sure you write this point so you don't lose unnecessary points. So like your teacher knows that you're not a complete retard and you know what you're doing. Once we get this, finally, we have all the numbers we need. H3 equals 762.51. All right. I'm just going to clean this up a little bit, and so we could solve the rest of the problems. Just give me a second. Okay, so now we have all the H's. We have everything we need to find these problems over here, okay? So, basically what you have to do is, we have to find how much water is going into the feed water, okay? So, keep in mind the equation that I said before. 0.2 and 0.5, all of the mass flow rate is equal to the mass flow at 0.3 and 0.7. So, H2M2 plus H5M5 equals to H3M3 plus H7M7. All right, so basically, keep in mind that a portion over here, Y, is leaving 0.5 and going into here, 0.7. And over here is 1 minus Y. So, that means over here it's equal to the total mass flow rate, 0.2, times 1 minus Y. Or, yeah, 1 minus Y. Plus H5. At 0.5, Y amount of the water is going into 0.7. So, it's equals to the total mass flow rate times Y. Y is just a fraction, okay? And it's going into 0.7. So 0.7 is the same thing. And then 0.3, it's going to be the same as 0.2. It's Y amount of water is going over here. And then the rest, 1 minus Y, is going over here from 2, 3. Okay? So H3 times the total mass flow rate times 1 minus Y. Now we can get rid of the mass flow rate. You're going to get H2 1 minus Y plus H5Y equals to H7Y plus H3 1 minus Y. Okay? Now the rest is simple algebra. You just have to factorize Y. I'm just going to do it quick. Y H5 negative H7 negative H2 plus H3 equals H3 negative H2. So then Y is equal to H3 negative H2, whoops, H5 negative H7 negative H2 plus H3. Now, sometimes in your practice or in your solutions, you're going to see them approximating H3 negative H2 divided by H5 negative H7. Some of your solutions, they're going to completely ignore this part, okay? You don't have to do that. This is a little bit more precise. It's just the reason why this approximation is used is because this doesn't make a huge difference. Well, hold on, let me fix it. It doesn't make, adding this part over here, it doesn't make a huge difference for your final value. And it just simplifies things a little bit, but I always like to do it because it just makes more sense for me, okay? you have all of the values that we wrote in the table up here. So finally, plugging in the values, you get a y of about 0.194. That means that 19.4% of the water is leaving the turbine and going into the 100% is leaving the turbine, but 19.4% is going into the closed feed water system. So finally, we can start calculating Qin. Qin is up over here from 0.4 to 0.3. So it's equal, and it's 100% of the mass flow rate. So H4 negative H3, which is equal to 3116.1 negative 762.51 to be about 2353.59 kilojoules per kilogram of water. That's our Qin. Q out is down over here. Now you can't just take H6 negative H1 because it's not 100% of the water that's in here. You have to take this into consideration, which we have. We just calculated 1 minus y. So 1 minus y times H6 negative H1. So 1 minus 0.194 times H6 2311.03 negative H1 251.42, giving us a Q out of about 1660.05. There you go. The net work is equal to Q in negative Q out, which we have all these two values over here. It's going to give us a value of about 693.54 kilojoules per kilogram. Okay. Lastly, we can find the thermal efficiency with Q net divided by Q in. 693.54 divided by Q in, which was calculated up here, 2353.59, giving us a value of about 29.5%. And that's it. The reason why usually in your solutions, they're not going to calculate the W out over here, which is W out. It's because you have to take into consideration the Y over here and the Y's over here, and it's a little too complicated. So instead, they use this formula over here, which is a lot easier. And that's it. That's how you solve your closed feed water systems.